Hello and welcome back to PC Retro Programmer. In this video we're going to be looking at the Verticalish case of the Bresenham line drawing algorithm. Now if you haven't seen the video on the horizontalish lines yet, I recommend watching that first because the assembly language and the explanation are essentially exactly the same for this version. In fact, there's not very much difference between the two versions at all. You remember that a horizontalish line is just one that is more horizontal than vertical, and a verticalish line is one that's more vertical and horizontal. And what that means in practice is that in the horizontalish algorithm, which is what we have here, we're always moving by 1 pixel in the x direction, the horizontal direction, every iteration, but we're only moving in the y direction if some condition holds. And so we just need to switch everything about. We just need to change the roles of x and y to get a verticalish version of this algorithm. In fact, it's equivalent to reflecting about a diagonal to switch x and y in this way, although you don't really have to understand that to follow this video. So let's just go through and naively switch x and y everywhere in this video. So certainly we'll need to now be increasing y by 1 every iteration, and we'll only want x to be increased if the condition holds, and we also want to switch the roles of dx and dy. We're basically just changing x to y and y to x everywhere here. Now we don't need to change the plot, that's not a function anyway, so this is not going to need alteration. And of course we'll also need to change the lead-in. This will now start at minus dy, and we'll start at the x-coordinate x0. And believe it or not, that's all that's required to get the verticalish version of this algorithm. We could also swap x and y here, but I'm sure that you can see all that'll happen is that you'll just end up switching these two lines around, which has no effect on the program. So that's everything that we need to do, and so what I've done is gone ahead and coded this up. Now there's a couple of ways we could attack this. Because we're now increasing by 1 in the y direction every iteration, we could use that regularity and the fact that incrementing y is actually a little bit easier in CGA than incrementing x. You don't have to worry about all those shifts for the pixels within a byte and worrying about the offset and so on. So we could actually take advantage of that and change the algorithm the way that we've implemented it to speed it up in this case. But just to keep this video simple, I'm going to go through and do the most naive thing that we can do and just switch around the bits of code that are relevant. So let's take a look at how that looks once we've switched everything about. Now in the horizontalish line drawing code that we've already implemented, we only did the case where we're moving down and to the right, and that actually won't change here. We're still moving down and to the right, we're just doing a verticalish line now instead of a horizontalish one. And we'll actually need additional cases of these algorithms for the down and to the left case, and we'll deal with that in a later video. So this verticalish code, I'm going to call this CGA line 2, and the introduction here is going to be exactly the same. Of course I have changed the assumption here, so dy is now bigger than or equal to dx because it's a verticalish line, but the register assignments are exactly the same, and the prelude here is basically identical. Now you might imagine that we need to start switching x and y all over the place here, but we really don't. The first thing that we're doing here is computing the parts of the offset corresponding to the x and y coordinates of the first point on the line. But the first point on the line is x0, y0, regardless of whether you're doing horizontalish or a verticalish line. So really nothing at all needs to change in this prelude here. Now I did have to move one piece of code further down, and that is where I was computing 2 dy here. I'm just computing dy now, and I'll talk about that in just a moment. There's one other change that we need to make, of course, and that is that the number of iterations is now dy plus 1 instead of dx plus 1. So this register here has to change to bp instead of dx. But otherwise it's essentially the same. And the other change that I've made here, which actually has nothing to do with the change to Verticalish, is because a viewer submitted a faster version of this piece of code. So we were using a sub with borrow and trick here in a previous video, which I explained. But Jim Leonard, one of our viewers, submitted this version instead and said that this would be faster. And I actually made an entire video. It was a really fascinating study to try and work out which of these pieces of code should be faster, if there's some way that we could know that without actually just timing the two different versions. And so I went through all of that, how you can actually tell, and we also timed it on 3 different CPUs, and indeed on at least on the 8088 and 8086, this version that Jim Leonard submitted is actually faster. So we're certainly going to use that from now on. Now the rest here is pretty much the same. The next change is to the initial d value. So that was minus dx before, that has to become minus dy, and that's just a change from the dx to the bp register, trivial change. And here is where I've moved that line which computes 2dy. I've had to move it down here because d now uses dy. So we can't compute 2dy until after that point. And so that means it literally has to be the last thing we do, essentially. So just to keep things nice and symmetric, I have both 2dy and 2dx now both computed down here. And the reason I'm doing that is because I'm thinking ahead to when I'm going to be combining these 2 versions into a single piece of code. And I want to be able to factor out as much code that's the same as possible, and pretty much everything from this point back, other than the iteration count, is the same in both pieces of code. So I may even want to move the iteration count further down here if I can, so that I can have even more code that's common between the 2 versions. Anyway, so that now brings us to the main loop. And there's not a lot to do here except to shift some bits of code about. Now of course the pixel plotting code is identical, and instead of adding 2dy to d here, we just have to add 2dx instead. So it's just a change from bp to dx register. Now inside the body of the if statement, instead of incrementing y, we now just have the code for incrementing x. Now there is a little bit of a change here. Remember that previously in the code for incrementing x, we were able to use the fact that STOSB already increments the offset, and so we were able to set this up in a tricky way to take advantage of that. We actually can't do that here because this increment x occurs inside the if statement, so inside the body of the if statement, and so it doesn't actually happen all the time, and so we wouldn't actually be able to use this to compensate for the STOSB. So we really have to do this a slightly different way, but it's really just the obvious thing. Basically the condition that we're interested in is when zeros get shifted out the bottom of BL and back into the top, and so the carry flag will be 0 in that case, and what we want to do is increase the offset by 1 byte in that case. So how do we turn a 0 carry into a 1 carry? Well, we just complement the carry flag. So that's what this little instruction does. So if it wasn't set before, it will now be set, and vice versa. And then we just use an add with carry 0 here, and so this will add 0 unless the carry is set, in which case it'll add 1. So that's the change that we need to make there, just because this piece of code is now inside the body of the if statement. Here we're just adding 2dy instead of 2dx, just a register change, trivial. And finally, here's the code for incrementing y, which has now been moved outside the body of the if statement. And now we still need to compensate for that extra increment that happens to the offset because of the STOSB above. And we just compensate for that by subtracting an extra 1 off di here. So that's it. That's all we need to do to change this code. There's the end of the loop and the end of the function. So that brings us to the main driver program. Now we actually do need to change the main driver because we need to make sure that we're drawing a verticalish line this time. So I'm actually going to draw from 00 to 100, 199 this time around. And that'll give us a y difference of 199, an x difference of 100, which is definitely a verticalish line. But other than that, everything else is exactly the same here. We just wait for a key press, restore the video mode, and terminate the program and go back to DOS. So let's save this and exit, and we'll assemble this, and hopefully didn't introduce any new bugs into our code. Looks okay. And we'll link it and run it, and hopefully we should get a verticalish line. And it looks okay. You can see we're going from the upper left, 0, 0, right to the bottom of the screen, which is y coordinate 199, and it looks like the x coordinate should be about 100 there, so I think we've been successful. So in the next videos, of course, we have to deal with those left moving lines. We'll always be able to draw the lines in the down direction. We'll just make sure that's always happening. We'll switch the coordinates around if not. And so basically, once we've dealt with that and we've merged everything into a single function for drawing lines, then we'll be done with our line drawing code.